Greetings, Chem 110H, Dr. Bevilacqua here to finish off the last of the periodic properties. We're going to look at reactivity trends, and we're going to look at acidic and basic oxides, and we're going to look at calcium oxide, which we'll see in an accompanying demonstration is a basic oxide, and we'll also look at phosphorus pentoxide, which we'll see is an acidic oxide. The reaction with calcium oxide and water is that it immediately dissolves, and it gives rise to the calcium cation and the oxide anion. The oxide anion can come in and it can lyse water or lead to hydrolysis, and it breaks this bond heterolytically. And when it does so, it gives rise to two hydroxides, one that comes from the hydroxide that forms from the oxide attacking, and one that comes from the hydroxide that's left behind. And this gives rise to it being a basic oxide because it generates hydroxide. In the case of phosphoric acid, it reacts with water and gives rise to this weak acid, H3PO4, and then that dissociates, being a weak acid, to give H plus and H2PO4 minus, and this is what earns its name of being a weak acid. And these properties arise because of the difference in the electronegativity between the two elements in the oxide. If we look at that, oxygen, being the second most electronegative atom, has a high electronegativity of 3.5. Calcium has a relatively low electronegativity of 1.0. Big electronegativity difference we'll see when it's greater than 2. It's an ionic compound. Electrons transfer, leaves us with oxide, and then that can lyse water. Phosphorus is more similar to oxygen on the periodic table. Its electronegativity is more similar. It has a smaller electronegativity difference, and this is molecular. The bonds are covalent, polar covalent, and so these bonds stay together, and this leads to an acidic oxide. And we can summarize that in this table here with acidic oxides over on the right, closer to oxygen, closer in electronegativity, and the oxides that form with elements on the left side are basic oxides. Here's a familiar acidic oxide, CO2. We saw this particular reaction in the voice-activated reaction where we passed around the round bottom flask in class, and that had in it a acid-base indicator, and we set that solution to be slightly basic when we pass it around. The CO2 that we exhaled formed carbonic acid, a weak acid, that neutralized the base that was in there and changed the color. So here we have a simple demonstration of basic and acidic oxides. Bob put some water into a crystallizing dish, along with some universal indicator, gives that a quick stir, and then he'll add a small amount of the solid calcium oxide, just a spatula tip full. And after adding that, he'll go ahead and give it a quick stir, and we see that the color turns purple. And when we consult the label, we see that the pH is greater than 10, so it's a basic oxide. Now we repeat with phosphorus pentoxide. It reacts right away. It's a more vigorous reaction, and now it turns the color a pink color. And when we consult the label, we see that the pH is actually acidic, or that it's less than 4, so this is an acidic oxide. And here we have them side by side. We can see the basic and the acidic oxide. On the previous slide, we were looking at anhydrides, and those anhydrides here on the left, they were basically bases and acids without their water. But we can go ahead and look at the reaction in reverse. Instead of starting with the anhydride, we could start with the acid and ask what is the corresponding anhydride. And I've picked here a series that we can follow on the periodic table from left to right: phosphorus, sulfur, and chlorine, and phosphoric acid, sulfuric acid, and perchloric acid. And when we remove water, in the center one we can simply subtract H2O. We're left with sulfur trioxide. On the right, we have to put a 2 in front so that we have 2 hydrogens to subtract. We're left with Cl2O7. And over here on the left, we have H3, so in order to subtract water, we have to put a 2 in front of that and a 3 in front of the water, and we're left with phosphorus pentoxide. And so this is how we can think about or generate the acid anhydrides of these very strong acids. And in fact, perchloric acid is a stronger acid than sulfuric acid. This perchloric has a pK of -10, sulfuric of -3, but they're both leveled in water, whose Bronsted acid H3O plus has a pK of -1.7, but in fact perchloric acid is a stronger acid. And the reason that we can understand that increasing acidity as we go from left to right is we have a better match in electronegativity with oxygen as we move across. And when that happens, then the oxygen is drawn more, the electrons in the oxygen are drawn more into the center atoms, and that weakens further the bond between oxygen and hydrogen, which is on the periphery of the molecule. So we can also think about anhydrides of the weaker acids. So I've got 3 weaker acids of phosphorus, sulfur, and chlorine here. Remember that we define acid strength as the difference in the number of atoms on the oxygen and the hydrogen. Here it's 3 minus 3, which is 0, so that's weaker than phosphoric acid, where it was 4 minus 3. Still both weak acids, but this guy's weaker. This is phosphorus acid. Here we have sulfurous acid, 3 minus 2, so that's weaker than 4 minus 2. And then we have hypochlorous acid, where we have 1 minus 1, or 0, much weaker. And so if we're interested in the acid anhydrides of these, we need to subtract out water, same game that we played over here. And when we do that, we get our corresponding acid anhydrides of these weak acids. In the case of P2O3, it actually exists as P4O6, which is a solid. So these oxides can give rise to acid-base chemistry, which I summarize on this slide. So here we have our basic oxide and our acidic oxide. So we can mix these two solids together, and just like in any acid-base reaction, it gives rise to a salt. It can't give rise to water in this case because there's no hydrogen. We can go ahead and we can hydrate the basic oxide, and that gives rise to the strong base calcium hydroxide. This will react with the solid acidic oxide and give rise to a salt, in this case water. When we balance, we see there's 3 waters. Alternatively, we can hydrate the acidic oxide and let that react with the basic oxide. That gives rise to the same 2 products. Or we can hydrate both the basic oxide and the acidic oxide, and now we have the familiar strong base weak acid reaction, and that gives rise to a salt and water. And we can summarize these reactions as shown here. The first reaction was between a basic metal oxide and an acidic non-metal oxide. The second reaction was between the the base and the non-metal oxide shown along here. The third reaction was between the metal oxide and the acid shown here, and then the fourth reaction was the familiar reaction between the base and the acid. So lastly, I'd like to go ahead and summarize the acidity of the elements in the periodic table. Here we have the third period in the periodic table. If we go ahead and let these elements react with oxygen, we end up with these oxides. The ones on the left are basic, the ones on the right are acidic. The ones in the center can be both acidic or basic and are called amphoteric. When we add water to these, we generate either bases, strong bases, such as sodium hydroxide, the strongest base on the left. This is a weaker base, this, remember, milk of magnesia. And then over here we have increasing acidity, the weak acid in phosphoric acid, a strong acid in sulfuric acid, and an even stronger acid in perchloric acid. Again, the ones in the center can be both bases or acids, and so they're amphoteric. The ones in the left will dissociate to give hydroxide ions as sodium hydroxide or magnesium hydroxide, therefore those are basic. Oxides, the ones on the right, will dissociate to give protons, and so therefore those are acidic oxides, and these can do both types of chemistry. Where does this come from? It all comes from the electronegativity difference. Over on the left, that electronegativity difference is big, and so the electrons are transferred. It gives oxide, which can hydrolyze water. Over here, the electronegativities are much more matched between the element and oxygen, and so they form molecular compounds that dissociate protons and are acidic. Thanks for listening.